All right, so happy Friday, everyone. Today we'll be speaking with Dr. Ben Kirtman, who is an internationally recognized expert on weather prediction. As background, Dr. Kirtman is professor of atmospheric science at the University of Miami. He also serves as director of the Cooperative Institute for Marine and Atmospheric Studies and deputy director of the Institute for Data Science and Computing. Dr. Kirtman is world-renowned for using complex computer models to bring unprecedented detail to climate change and weather prediction, and that's what we're going to be talking about today. Professor Kirtman also serves as an advisor for the UN, has a leadership role in the World Climate Research Program, and has chaired the International Working Group on Seasonal Interannual Prediction. Dr. Kirtman was a coordinating lead author on the Intergovernmental Panel on Climate Change and is executive editor of Climate Dynamics and several other leading journals. He has received numerous research grants from the National Science Foundation, Department of Energy, National Oceanic and Atmospheric Administration, NASA, and the Office of Naval Research. He also leads the North American multi-model Ensemble prediction experiment. He is author of over 130 peer-reviewed articles, is a recipient of UM's Award for Scholarly Activity, and was awarded the Undergraduate Teaching Award 3 consecutive years. He is a fellow of the American Meteorology Society and here to discuss the SUBX, the subseasonal experiment, which is absolutely fascinating, and really how accurate can weather prediction be moving forward. So again, Ben, thank you for joining us. Really appreciate your time.
Thank you, and thanks for that generous introduction. I appreciate that.
Well, it's a lot of accomplishments, and obviously you deserve all the credit. First, I just want to talk a little bit about how you initially got interested in weather prediction. I heard it was a pretty interesting story.
Yeah, my interest dates back to when I was a kid, and we lived in Southern California, and our every time there was an El Nino, there typically is a lot more rain in Southern California, and our house was right at the water table, and we had a small basement for the water heater, and of course, when there was an El Nino, the basement would flood. And my father was very frugal, and so he bought a pump based on the Bernoulli principle that required you to stay awake while the pump was running, because if you went to sleep, the pump ran dry and it would break. So my job as a teenager up until I went to college was to babysit the pump whenever there was an El Nino event. So that's how I got interested in weather and climate. Of course, when I went to college, he broke down and bought an electric pump that didn't require supervision.
Well, I mean, it's a great story, and obviously it's an interesting way to kind of get involved and how times have changed since then. How do we currently predict weather? Just give us a brief overview of what's the current situation.
Sure. So there's basically 3 big ingredients. The first big ingredient is that we go out and take observations all over the world. Those are with satellites, with balloons, drones, all kinds of different instruments. All that data is collected in real time. And then the second step is to map all that disparate data on irregular spacings, to map that into a data set that models can use to make a forecast into the future. That process is called data assimilation. That sort of fills in the gaps where data is missing. And then the third and final step is you put that state of the climate system today into a sophisticated computer model, and you march that forward 14 days or so, and that produces a weather forecast.
And everyone always complains about how weather cannot be accurately predicted. But in your opinion, how accurate is our current system?
Well, right now our forecasts out to 7 days, we do a remarkably good job. There's theory to say that after about 14 days, the day-to-day weather fluctuations on a regular basis are going to be pretty tough to predict. And that's because the climate system is chaotic. And, you've heard that old story, a butterfly flaps its wings in Argentina and that changes the weather in New York City. There's some truth to that. Small, tiny changes or small, tiny errors in our observations or small errors in our model ultimately give a forecast that loses all skill after about 14 days or so.
So in your opinion, what is the biggest limitation to accurate long-term weather prediction?
So the long-term problem that you're referring to is, why do I say I can do something at beyond 14 days, 3 weeks and 4 weeks? And there I'm talking about predicting shifts in the statistics of weather. And there's lots of reasons to think we can do that. There's slowly evolving things in the climate system, mostly related to how the ocean works, but there are slowly evolving things in the climate system. If we can predict them, then we can predict how they affect the statistics of weather. So can I say, during hurricane season, 3 weeks out, actually, we're going to enter a period where it's really relatively quiet. But then beyond that, we might enter a period that's really active. So it's sort of talking about predicting the statistics of weather forward in time.
I mean, and let's talk about ways to kind of hopefully address all those limitations. And that's what you've really focused on, and talk about the SUBX experiment, the subseasonal experiment. What is that? What is it trying to address?
So the SUBX experiment was started a few years ago. As our models improve and our understanding improves and our data sets improve, we've learned that this time period, this week 3 and 4 out into the future, has always been viewed as impossible. We could never do anything. But our models are getting better, our understanding is getting better, and we've discovered that there's a lot we can do predicting what's going to happen 3 or 4 weeks into the future in terms of what we like to call forecasts of opportunity. So are things coming together so that we can actually say, okay, California or the West Coast of the US is going to get a lot more atmospheric rivers that produce that intense rainfall that we saw, or that there's going to be a huge cold air outbreak in Texas 3 or 4 weeks from today that's really going to drive things crazy. And even there's some evidence that we might be able to say an individual hurricane at 3 weeks or something like that. So there are lots of things that our science is telling us we can actually predict beyond this so-called week 2, 14-day chaotic limit of weather predictability. So it's talking about predicting the statistics out there. And traditionally, we thought this, when I was a graduate student, there was no hope of predicting this time scale, but the field has evolved, and we've learned a lot of things, and we can actually make predictions now that are useful.
I mean, so amazing. Who's involved in this project, and what are the groups?
Yeah, so this is a real big project. It's funded. It was initially co-funded by NOAA and the DoD and NASA, but it involves groups from Canada, the Canadian National Weather Service. It involves Navy modelers, modelers from the National Center for Atmospheric Research, modelers from NASA, and modelers from NOAA. So it's a big project, lots of moving parts, lots of people involved, but that's part of the excitement. And that's one of the important things in bridging this longer timescale, this week 3 and 4, is that we need to use multiple tools to multiple models to make these forecasts so we can get a better estimate of what the range of possible outcomes are. And so these projects are necessarily big projects with lots of moving parts.
When did you first, when was this first started? When was it first implemented?
I think we started in, I think the overall project started in 2018. That involved a couple of years. You have to launch these projects, you have to forecast the past. It sounds funny, but we do all these experiments to forecast the past to measure how well our models do, to calibrate them, to do skill estimates, to ask questions about what we're doing wrong, what we're doing right. And somewhere around 2020, we launched the real-time phase, where we're actually doing these in real time, and they're given to the National Weather Service, and they're used by National Weather Service forecasters to make their week 3, 4 outlooks. And the private sector has started to glom on these things, and people are using them to make forecasts, to make money and think about investments and all kinds of things like that.
Wow, truly amazing. And what, again, is your role in this? Are you the director? This was your idea. You're overseeing it.
Right. So the project is, a proposal had to be written. So I was the principal investigator of the proposal. I cobbled together the team. I lead the day-to-day. It's got to get, the forecast has to get out. One of the challenges for someone like me who works at a university, the program requires that forecasts be delivered on time, all the time, without fail. There's no and for a university professor to do that is kind of unusual. It's not the standard thing. So, making sure we have a lot of machinery in place that make sure we can deliver on time all the time without failure. In fact, during Hurricane Irma, we were still trying to deliver forecasts, and we had to come up with some pretty crazy ways to deliver on time.
I mean, it seems like a huge responsibility, and obviously this is something that you've seen through from the initiation all the way to kind of mainstream now, and we'll get into that in just a little bit, but give us some examples of how the SUBX project successfully predicted natural disasters or large weather events.
Well, we were, of course, the one I mentioned earlier was the cold air outbreak in Texas. We knew three to 4 weeks in advance that huge cold air outbreak in Texas was going to happen. The models all converged, and we have a great deal of confidence. Now, in that particular example, some of the challenges are to get people to use this forecast information to think about how to move energy supplies to, oil to cover the heating costs and, things like that. So there were some big issues in Texas in terms of how to respond to that information. But there have been cases where resources have been redeployed based on these SUBX forecasts. One of the earliest forecasts that we made involved some heavy rainfall in Atmospheric River in California that led to mudslides in Montecito and unfortunately some fatalities. And so we do make these forecasts, and we hope that people are going to use them to make decisions. I believe we did pretty good, even capturing hints of Hurricane Matthew recently. So there are, a number of case studies. It's not perfect. There are things that we miss. So some of the heat dome in the West this previous summer, we did miss, which surprised me a lot. So there's some work to do there.
Yeah, I mean, nothing's perfect. And I just want to summarize for everyone who's listening, but the goal is to accurately predict large weather events 1 month in advance, which currently, like to most of us, seems impossible. How does your model, in just layman's terms, how does your model accurately predict large weather events 1 month out?
So it's a really good question, and trying to put it in layman's terms is not as simple as one might think. Yeah. There are phenomenon that happen in the climate system, and one of the key ones is called the Madden-Julian oscillation, and it's a thing that happens in the deep tropics where there's large scale precipitation occurs in one region, and then in another region the precipitation is suppressed. This thing moves around the equator very slowly. And when that moves around the equator, that disrupts weather patterns around the globe. And it moves so slowly that if we can capture that, we can capture its disruption of weather patterns around the globe. And so that affects rainfall over North America, for example. And so if we can predict that, and that's what we're trying to predict, we capture the disruption of weather patterns which produce extreme events all around the globe. And so that's really why we think we can do this. And this is where we have found successes.
So, now that it's gaining traction and it's becoming more mainstream, talk a little bit about how you would like to see this implemented, meaning the impact on society, being able to accurately predict heat waves, floods, droughts, fires, hurricanes, all well ahead of time, in terms of preparation and planning. What would you ultimately like to see this do and be done with it?
Yeah, what would be great is if people, if we could build those trust relationships, that people understand what these forecasts can do and can't do, and that they're necessarily probabilistic. So in other words, we're saying that there's a 70% chance of a extreme rainfall in the Southeast, for example, in week 3 and 4, something like that. And then people can then make investments in resources to deal with those challenges, or, again, a 70% chance of a cold air outbreak in Texas, and they can make sure they have places to provide heating for people who don't have adequate heating supplies and things like that. So that's what we really want to do. One of the really difficult things is getting the communities, the boots on the ground that are making decisions about moving resources and making investments, getting them to look at these forecasts and trust these forecasts. And that's not a, we throw the forecast over the fence and everything's great. It doesn't work that way. That requires an iterative process. They want, oh, no, we want you to produce the forecast in a different way. We need to look at a different variable because that motivates our decision process. And so we need much closer interaction with the people that are making decisions. That's challenging. That's really hard work. It's hard for people to find the time to do it. And that's what we need to do.
So let's talk about that trust issue, because that really is important, right? You guys clearly have a great model. It's being vetted. It's shown to be accurate, but how do you gain the trust of public? Is it just simply data and more data and more data?
Well, that's a big part of it, but I think a big part of it is also working with people that make decisions. So it could be the farmer, the orange farmer in Florida who's worried about an early frost. We have to figure out how to reach into those communities, educate them about our capabilities, but also equally important, really listen to what they need in order to make decisions that will make them more profitable. And that interaction and exchange is something that's hard to do. It's hard to figure out how to set that up. It's a case-by-case basis, so it can be really demanding, but that's what needs to be done.
Yeah, I mean, it sounds like it really needs to be a grassroots effort almost.
Yep, that's right.
So it's not just getting the trust of NOAA or NASA. It's really grassroots, the people, with just boots on the ground, making decisions at that level.
It's exactly. The most important thing is that from my perspective, a forecast is useless unless somebody is making a decision based on that forecast. And so we need to make sure people are understanding these forecasts and using them to make decisions in a way that makes their lives better, their jobs easier, they save lives, save property, whatever it is.
Yeah, I mean, it sounds like the way to do that is just the way you're doing, basically demonstrated accurate predictions over and over and over again. And if you're shown to be accurate at a very high rate, then eventually people are going to be listening and they're going to be trusting you. But it's a tall order, obviously.
It is. It's very hard to do. We in the physical science world, we always underestimate how difficult it is to build those trust relationships so that people will use your forecast.
Now let's talk about what novel technologies you're using, because this is such a breakthrough in terms of weather prediction. What type of supercomputers or novel technology does SUBX require?
Well, one of the things, I think the big direction that we're really going that's novel is the use of data science, machine learning, and artificial intelligence. One of the things we're working on at the moment is, can we understand when a forecasts are correct, when they're right, when they're really good, can we understand the processes that went into those forecasts to make sure it was correct? And then alternatively, when the forecasts go bad, can we look at why did it go bad? What model errors produced a poor forecast? And we use machine learning and artificial intelligence techniques to start to do those things. And figuring out how to combine these forecasts from all these disparate models to make a better forecast, that often involves machine learning and artificial intelligence. The big breakthrough, I think, that's coming, even beyond what we've already done, is the use of machine learning and artificial intelligence to make these forecasts even more useful than they already are.
So I definitely want to, just talk about that more because it's so fascinating. I was going to ask you, how can this model be improved? And it sounds like you just led into that. Basically, this model combined with AI to just over time build that experience and just continually become more accurate. Is that correct?
Yeah, that's what I think the next breakthrough is going to be, is the really clever understanding and blending of artificial intelligence and these dynamical models, computer models, to produce the best possible forecast. And I've already, in our group, we're already seeing really big hints about understanding. One of the things we're looking at is weather in the Southeast US and the rainfall in the Southeast US. And we're seeing very different processes going into successful winter forecasts versus successful summer forecasts. And using that learning will ultimately allow us to make better forecasts.
Is your group also leading the way when it comes to AI and weather prediction?
I don't know. Everyone, I can't claim we're leading the way, but we're certainly part of the tide. There's clearly a big tide in using data science to advance the physical sciences. The Institute of Data Science and Computing at the University of Miami is just a tremendous vehicle for really pushing those boundaries. And so having that facility so readily available is making a big difference. I'm not going to claim world leadership today, but maybe I will try to claim that leadership a couple of years from now.
That's great. That's great to hear. And it's wonderful, to hear about UM's collaborative effort. And it's obviously a wonderful university with so many strong departments, and to hear what you guys are doing is just obviously makes us very proud. You guys are making grassroots efforts. You're pushing this model, which is going to be very successful. What about on a national level? What about even more on a global level? How are you guys attacking that? Or is that something that's in the future? Once you gain the local, then you go national. Once you go national, then you go global.
Well, the national and global is happening already. So the National Weather Service uses our data in order to make their week 3-4 outlooks available to the public. So that's one of our biggest customers. But we also make our data readily available to the entire international community. And so we're aware of it, but we don't. There's so many people following it. We're not. We don't keep full tabs, but a lot of people are downloading our data and they're using it internationally also. We would love to keep tabs on it. Occasionally we send out an email to everybody who's grabbing the data. Tell us about how you're using the data. But we do know that there are a lot of groups internationally that are using it. The international research community has a big effort on this timescale. And so we're starting to see those two efforts sort of come together intellectually anyways. And the international effort is starting to use a lot of our data, and it's all housed in similar places.
So, kind of wrapping up here, because I know you're super busy. If you had a crystal ball and you could look at weather prediction currently and then compare that 10 years from now, 25 years from now, and let's say 50 years from now, are we ever going to have 100% accurate weather prediction?
No. Which is a good thing. Otherwise, I wouldn't have a job, right? You need guys like me to figure out how to bring together imperfect prediction systems in order to make them better. But the fact that the climate system is chaotic and the butterfly flaps its wings ultimately means there'll always be forecasts going out into these kind of lead times will always be probabilistic. The best we'll ever do is say, there's a 70% chance of this, a 60% chance of that. And when we say that, there's always a 40% chance that you're wrong, right? So there'll always be some inaccuracies that we just have to learn how to manage that risk.
But you think a month out prediction is definitely feasible. It's happening currently, and it's only going to become more accurate with the incorporation of AI and other supercomputers and technologies.
That's a great way to summarize it. That's absolutely true.
Wonderful. Listen, Ben, pleasure speaking with you. Amazing work that you and your group are doing. Kudos for leading the way. UM leading the way. And this is an amazing technology that, like you said, is going to help millions of people. If you can predict weather disasters weeks in advance in terms of preparation and planning, this is really a true game changer.
Yeah, thank you. Thank you for having me. And I'm really, really pleased to talk about this project, and anybody who's interested should reach out to me.
All right, Ben, you have a great day. Take care.
You too. Thank you. Bye-bye.